Hello and welcome everyone to the short video abstract of our recent work on the stochastic thermodynamics of an inertial Stuart Landau dimer. Our starting point in this work is a model for Hopf bifurcation and limit cycle oscillations, known as the Stuart Landau model. We first extend the standard damped Stuart Landau model to the underdamped regime, accounting for the inertial-like term and incorporating Gaussian white noise, whose strength obeys the fluctuation-dissipation relation. The model you see on your screen ensures that the two oscillators of the dimer synchronize in specific parameter regimes, and the presence of noise indicates that the synchronizing model is connected to thermal reservoirs. In the zero temperature limit, wherein the oscillators experience no stochastic force but are damped, we find that the phase diagram of our underdamped Stuart Landau model shows a rich, complex behavior. It exhibits out-of-phase synchronization as seen in panel E. The model also shows bistability as marked by the colored regions in panels A and B. At any finite temperature, there'll be stochasticity, and all signatures of the zero temperature behavior are wiped out, as seen in panels G to J. We then develop a stochastic thermodynamics framework to identify physically meaningful heat and work. Surprisingly, this is done in a frame in which each oscillator is rotating such that the inertial-like Stuart Landau dimer can be mapped to two charged particles in a magnetic field. In this frame, a single oscillator follows the equation shown on the screen with the potential described by U of modulus C. In this rotating frame, a single oscillator is actually in equilibrium, but appears to be in non-equilibrium in the original frame of reference, exhibiting limit cycle behavior. Such an equilibrium description sets a reference and hence is key to formulate stochastic thermodynamics. Once we identify the physically meaningful work, we show that the work output of such a continuous time machine is maximized when the system is in the coherently synchronized phase, as denoted by CLCI. In the bistable regime, the work output can show a hysteresis in the temporal metastable regime, which is marked by the black lines. The machine outputs the least amount of work when the two oscillators are incoherent and unsynchronized with each other, marked as ILC. Importantly, in the synchronized regime, when the work output is the highest, the reliability of the machine is also maximum, making it a powerful and dependable machine. Our work highlights the importance of coherently synchronized working substance in the performance and output of a machine. An interesting future direction would be to study a large network of underdamped oscillators rather than a dimer to see whether the machine performance can be further boosted due to the emergence of synchronization as a collective behavior. With this, I'd like to thank you all for listening, and we hope you enjoy reading our work.